Bismillahirrahmanirrahim. Assalamu alaikum. So far we have considered specific kinds of planar dynamical systems, which includes like x prime to be lambda 0 0 mu times x. This was discussed with the cases that when lambda and mu both are negative, both are positive, and one negative, other positive, what was going on. We have discussed already. Secondly, we discussed that so in this case A involved is lambda 0 0 mu, and then we considered this x prime to be alpha beta minus beta alpha x, and in this case A was this, and we have seen that if alpha are 0 then we had purely imaginary, and if alpha were non-zero then we had complex, and the behavior was sink spiral or spiral source or spiral sink. And in this case A is alpha beta minus beta alpha, and then we finally in the last video we discussed x prime to be lambda 1 0 lambda times x, and in this case A involved is lambda 1 0 lambda, and in this case we have seen that the eigenvalues were repeated, and if lambda were greater than 0 then origin was kind of unstable, and if lambda was less than 0 then the origin was uh, less than 0 stable and greater than 0 unstable for this case. So all of these matrices are very important. They are said to be in the canonical forms. Canonical forms. They are said to be in canonical forms. But what if we have other than these three matrices? What happens if we have, for example, let's say I have matrix this 1 2 9 8. Now this matrix is not coming in the category of these three, though we have seen some examples where we don't have these particular forms, but like now we are going to do this in a formal way, that what will happen, what can we do if the A is not in canonical form. So the linear transformations are very helpful. Then what we can do is we can define a certain transformation that can put this A into uh, one of these forms, canonical forms, and then we can study. For example, I have this system x prime equal to this 1 2 9 8 x. Now I know that this system is not in the canonical form, but I can define a certain transformation, a linear transformation. With the help of that I can throw this particular system into an other setup or another form where this matrix becomes one of these forms, and then I know about these forms already. Okay, and then I can study the behavior over here. So the behavior that is over here will going to be same over here. So let me define linear transformation. Okay, linear transformation. So from linear algebra you know what is a linear transformation between two vector spaces, but now I'll be specifically talking about t from R2 to R2 is said to be linear transformation if what happens if t is of simply this form, a operating onto some xy gives me ax plus by and cx plus dy. In other words, it is matrix times some vector. So a linear transformation from R2 to R2 is nothing but a matrix. When this linear transformation is invertible, when the transformation will have inverse. So well, t is invertible, or you can say T inverse exists if the determinant of this T, I mean this matrix A, B, C, D is non-zero. Okay, or even you can name this matrix T, because now R2 to R2 T is transformation is nothing but a matrix. So t will be invertible if determinant of t or the matrix corresponding to t will be invertible. So determinant is not 0. Okay, so now, so this is basically the proposition that t, which is a b c d, now this is transformation from r2 to r2. So there is a proposition which says that t is invertible. T invertible means T inverse exists if and only if determinant of T is not 0, which is the same thing as I mentioned earlier. Okay, now we have an interesting thing. Now consider this system y prime to be T inverse a t y for some transformation times y. Now consider this dynamical system. Now if y of t is solution of, let's say I'm calling this star, is solution of star, then x of t defined by a times the solution y of t will be solution to x prime to be a x. That's very interesting that if you have solution to this system, then you just multiply it with a and you get the solution to this system. Okay, so a is, oh forgive me, sorry, this is ty. So if you have a solution to this system, then my t will do what? My t will transform my solution to this system to solution to this system. So t is doing what? So t is basically doing one thing. T is taking the solution of this system. Okay, t is doing what? T is taking the solution of this system and it is throwing the solution of this system to, or in other words, t is helping me to find the solution to this system from this system. So given system of this solution of this system, my t will give me the solution of this system. Okay, so what will t inverse do? So T inverse will do what? T inverse will take the solution of this system and will give me the solution to this system. Okay. So now let's prove this small thing. So my y of t is solving this. So my y of t is equal to ty of t is equal to x of t. So I am taking the derivative of this all. Okay. So this will give me t y prime, and which is giving me t times y prime is t inverse a t y, which is t inverse a t y. But this guy is identity, so this is a times ty, but ty is equal to x, so this is ax. That means that x prime is ax. In other words, x prime is ax. So that shows that if y is solving this, then ty will solve this. Okay, so y solves this, then ty will solve this. This is t times y. If y is solving this, then ty will solve this. Similarly, if x solves x prime equal to ax, then t inverse ax will solve y prime equal to t inverse a t y. Okay, so this is what you need to keep in head, which in fact you can show. If x solves x prime to be ax, then t inverse x will solve y prime to be T inverse A T y. How can we do that? So set y of t to be equal to T inverse x. Now apply derivative. So this is going to be T inverse x prime, and then T inverse x prime is ax, but I can multiply t and inverse t. So this is going to be T inverse a t, and then this is nothing but y. So you can show that if x is solving this, then T inverse x will solve this. So far that's it from my side. Now in the next videos we will be using this theory that we have roughly discussed now.